So it's set up a bit differently than what Nick did. I think just to follow on from what Nick said, we do want the highest signal-to-noise ratio pulse profiles we possibly can get, but I think more importantly is we want the best pulse profiles, right? So the signals we're looking for, a lot of them are very tiny, right? So for gravitational waves, they're going to get pulse around 10 by 10 nanoseconds. If you imagine you had a pulsar with a spin period of even 1 millisecond, right? What fraction of the pulse spin period is that? Right, so we typically take data that's got maybe 1,024 bits across the pulse profile. So a millisecond divided by 1,024 is a microsecond. So 100 milliseconds is a 10th of a pulse spin. 10 nanoseconds is a 100th of a pulse spin, right? So when we think about time taking, we need to be able to measure changes in the pulse profile that are shifting it in time by 1% of a pulse, right? So this is kind of crazy, but it's doable, which kind of makes sense. So, but we want to be able to be sure that anything else that can be working out pulse profiles out there, so, right? So, our argument about having high signal-to-noise ratio is good, having high fidelity is better. So, anyways, so what we're going to do is there's a few different sort of steps that we can do here. There's this first little bit here is about trying to assess basically how well we can time this pulsar. So the data that we have for this exercise comes from Meerkat. It's all the data taken on this pulsar that Nick mentioned earlier, 1951 and it's all data taken up until I grabbed it last week. So the first method is just about looking at the data, using some of the commands that Nick mentioned earlier, and thinking about how well we want to be able to time it based on the period. So I think, so this is using this PSR set, and the next bit is about adding data together, as Marissa said. And we might start with that afterwards. Just because I think it's probably good for us to both that together. And especially for our less familiar with like mixed scripting commands. This thing, you want to do just an official way. So we'll do that. We'll skip 2.3 and then do this step here, which is generate this template using a interactive tool. And then finally, once we're done with that, we'll generate ToAs using CAT. And here's John asked about different algorithms, and this is FDM here, which is before you name it. But there's other options here, and it'll be interesting to go into that. So, I mean, you might just, we've got a couple minutes. People have, who has data on zit? Okay, so I'm going to try to just to see if things are working and if things are visible for you guys. Right, okay, so everybody's on zip data, and so you both. So do you have directories like data and data system channels? Yes or no? Or both? Yes, thumbs up. I don't know. You don't have to. Okay. So yeah, so what we're going to do is we're going to focus at first on using they contain the same observations. One set of data is what we call frequency average, so that's called, we call it And this way we test all our virtual machines. I'm a bad example, and I don't have a virtual machine. I'm just logged into a supercomputer in Australia, so it seems to be for that. But the first thing let's do is let's try to get data that we can use to make a template. So you can see here, if I do ls j star AR, these are all the observations I have. And I do WC, which is word count for the units which channels are wet. And it says that I've got 109 observations. So if I was to add up all of these, I could add up all of these observations and make the best profile ever for doing the profile making. But that might take probably 20 or 30 minutes. Maybe you want to do that over lunchtime and see what happens. Plug your computer in so it doesn't go dead. But just for now, I'm just going to add up the observations from 2023. So to do that, I'm going to PSR add -o add.ar, right? And you can call your observation whatever you want to call it. And so now I have these observations, and I know this based on the naming convention that goes Pulsar name, that here is telling me the start from the observation, right? So 2023 09 12. So this is an observation from, a couple weeks ago. But I only want the 2023 observations. So I do 2023 star.ar, and then I'm only adding up those observations. So right here now, because of the way, Linux or like operating systems work, you can name your files whatever you want, and based on the mirror pipeline, you see here I've got zap. That means this observation has been cleaned ORFI using Pulsar. FTS means that's been frequency averaged, time averaged, and converted into Stokes parameters. And .ART means that's just a file extension. Oh, and finally, the delay, DLI, means we've corrected for some instrumental delays within the Meerkat system. That over the course of the system, there was different time stamping and things like that. Okay. So you can see here now, I've got my added observation together. And now take a look at it. So how people made random observation as well? We can move on to section 2 and 4 now. And this is an interactive model for so if you want to try cost minus I for interactive minus the 1/xs AR. So the I is making it interactive. This is telling you a window to put it in. And this is the file. Okay. There you go. Okay. So now you can go to the interactive window. Now, what this is going to do is we're going to be adding, basically, modeling the profile as a bunch of Gaussians. We call them quantum basis functions because they're Gaussians that are periodic on phase 0 to 1. So what you need to do is interactive today. So if you want to start making a best guess of what the profile looks like, by having interactive successive Gaussian. So there's 3 parameters for each Gaussian. There's the center, the width, and the amplitude. So the first now it will do a linear, will do denominator fit if I now type F in the journal. Okay? Let's see, you know, see that. So if everybody goes to try to do that. So with the mouse, left click 3 times. One where you think the center of the component is, one where you think the width is, and one where you think the height is. So what you can do is if you actually have one, you can say, oh, I'm going to find another one over here. I'm going to fit for its peak, its width, and its amplitude. There. And now I type F again. And now it's fitted with that. And now I say I'm going to come over here. This red line here is the residuals. So I can do that. I can fit forward here. And you can see I don't have to be super accurate. Because I'll hit fit and then the fitting will add extra components. Right? So we can see how this is working. You just keep adding things for a whole. Right, I think another thing you should also make sure is that we're adding Gauss states. It's quite obvious that pulsars aren't Gauss states because there's still leftovers. Okay? So we can do this in a lot of different ways, and we still have obviously excess noise given data set present here. So if I'm happy with my template, I can type S to state it. Well, that's one of the things that we're going to look at. We're going to be looking at how perfect we need to be and how to talk about the quality of that. For now, we can just S. I think a Q. What we're going to do is
I'm going to just stick some numbers in.
Run this thing called Hog. And Hog allows you to call this thing, right? Color 1, color 2, color 3, color 4, and then so what we're seeing here now is what we're just talking about. What is this is the file name going into away from. This is the observing frequency. So what do you notice about the observing frequencies? Are they the same?
You can show me.
They're similar, right? Does anybody know why they're different?
Yes.
Because we've done a bit of different products happening. If this has a catalog that's bringing the version machine before, and we've got their cat data. So, I guess before we show you anything about what Tempo2 does, let's just talk about data. So this, if we had a good model for the data, what would we expect to see? Zero mean, right? And when we're talking about zero mean, we also circle small residuals relative to the error bars, right? So this plot here is showing you the residuals and the error bars. And in the case of my data, you can't use the error bars because it's the model, because something's wrong, right? So what do we think is wrong? Because a lot of different things are wrong, and sharp is the way to a lot of answer. So what's the biggest thing trend in data? Right, so it's going down this way. Sorry. It potentially could be, but in this case, it's not. To see the highest and effects, what we use, we can do this on other terms. So, any other? Yes. Close. You know what is P dot? So we were talking model where we've got different components. So you've got we'll call frequency and frequency derivative. And if my spin frequency was wrong, what would happen? It would drift away. If my frequency derivative is wrong, what would happen? It would drift as well, but in a different way, right? It would work a different way. Whereas that's not the way to think of it, right? Yeah, okay, so we'll say, okay, we'll get to that in a bit, right? We'll say the biggest thing is this, right? And I'm going to show this in a way that's not necessarily the way you would do the timing, but just to show you what affects me. So what you want to do is, for the first one, we'll go up here and hit, left click hit F0, okay, and hit refit.
And just to remember what F0 is.
Ooh. So we got, we have different parameters here, so right, we'll go through that. So we have RA, right section, def is destination, F0, F1, frequency derivative. If I did F2, what would that be? Yeah, F3, etc., right? DM, PMRA, what plus RA, right section, PM, proper motion in right ascension, PM tech, makes sense? Sin I, B, A1, task. So these are binary factors, so we'll get most of it. Okay, so we hit F0, you hit refit once, right? Only once. Now go and get most of it. Yeah. The other thing you can see here is there's a lot of information. There's a wealth of information that is recorded both in the terminal, like down here and over here. So you can see stat delays like models of the solar system ephemeris and stuff down here. Okay, so everybody, we hit once, right? And if things go bad, you can always just hit quit and start again. It's not like you destroy your ToAs and destroy the universe.
Or restart.
Or restart. I'm a bit nervous. Okay. So now, everybody has something that looks like this, right? Your error bar is probably a bit different than mine because I did that one. Okay. Cool. So the next thing we can do is we can look and see how our data, we can put on the x and the y-axis different things, right? So we can put on things like orbital phase, right? So this pulsar is in the binary. So now you can see how your choice is orbital phase. Serial. We just added data here. That looks kind of interesting. Frequencies look kind of crazy just because we're all choosing the same frequency. Year is nice as well because it helps you have a sinusoids and interesting periods. And then just other things as well. But what we might do now is, so what we see here is something like a sinusoidal, and you have a rough estimate of the period of that. So if I go over here, I can tell you that the binary period of this pulsar is 11 days. Is this 11 days? Right? It's the peak here is just before 2021. The trough here is before 2021. The trough here is before 2022. It's, what do you think that's at? A year, perhaps? Right? So one of the things that would be wrong, right? We're sensitive to is the motion of the earth around the source of the very circuit. That allows us to measure also positions to very high altitude. So what I'm going to do now is I'm going to fit also for F1 because that's probably also wrong. And then fit for RA and XL. And now hit refit once. We'll see what happens. Okay. And so what you see here is that I went from having over here, this is telling me how good my fit, well, it's good fit is the hardness and residuals go from 32 to 12, right? 12 microseconds. So it's improved quite a bit. So do other people have things that look similar to this now? No? Yeah? It looks like this, right? Things look kind of just random. We can now see our error bars at least, right? But what you can say here is that the reduced height, it looks kind of like white in the sense that there's no correlated structure on these very large time scales here, right? But the reduced pi squared is very bad. And you can see here, it's recorded up here. As we want this value, we want this value to be close to 1. That's 4.3. Pretty bad. Okay, so what are we going on now? So then we plot here versus orbital phase, and you see this. And you can see here this big structure. So this is going to be some combination of the orbital period, PV being wrong, the projected setting major axis A1 being wrong, time of the ascending node. This is when the orbit is coming, the pulsar is coming directly towards us on one side. And in this model of this binary model, these parameters of GPS1 and GPS2, and they're telling us about the eccentricity of the orbit and its orientation with respect to what. Okay? So we all have those all fitted, and now we fit enter again. Boom! Okay. Looking pretty good. Oh, okay. Giving some away. Okay. So what we can do now also is see like how different parameters have gone. You look down here and see how much this has changed. And you can see how significant changes in different parameters. So you can see here that one of the biggest changes actually was to this parameter here, which has to do with the as you can see. Okay? So now things are looking interesting okay here. Our reduced chi-square now comes down to still it's 3.2. So ways to go. So now we go over this again. And now we've got correlated structure again now versus time. So this is kind of a weird one though, right? Because it's like a combination of a tray going up like this. But then you can also kind of see something that looks like it's wiggling at a period of about a year. Anybody hazard to guess what could be causing that? So if the position was off, right, it's a pure digitous language. So what happens if the position is flying here but wrong here? It's fine sometimes and not fine other times. Yeah, it's moving. Also, it's moving. Curling through the galaxy at a clip of 50 kilometers a second, which is pretty average for a pulsar. So what it probably has is it's like this proper motion, right? And we so it fit this thing. So you can make these better or worse? Or have you already tried? Do you already know the answer? Whoa! Look at that. So anyways, does that look off? So okay, well, folks, does that look good? Bad? Ooh, oh! That is bad. Well, it's good. That's bad. It's too good, right? So we notice now is that we've got another thing. So we have a proper motion. Yeah, so it went from the headlock was 8.8 to 6. But you can see here, like, the incredible precision that we measured the power motion. So even though it only went by, changed by 1.5 million arcseconds per year, all that structure went away. So I said that I was, look at this now. So that's okay. So how does that compare to what yours look like? Is there any differences? Right. The issue for me is that if I was to look here and look at the error size relative to 0, it's pretty big. So I think that the reduced chi-square is we'll see it in my right, this is my reduced chi-squares. Anyways. So we'll plot this now. Now go back to first orbital phase. So now here, the structure here. And the structure is likely related to the Shapiro generated pulsar. So as the pulsar companion, as a pulsar like its companion, it experiences a gravitational delay as the radiation travels through that gravitational field. And because of covariance between the parameters, it's kind of showing that it's 20 pulse phase, but what we do is try to get M2, so that's the mass of the companion. And we get 3 to there. Okay? So it's looking a lot better now. And now we can be brave and hit for sign on as well. So that's so basically I've assumed for that first bit what we had is we assumed that the inclination angle was something like 85 degrees. But we also fit for that. And the shape, depending on the inclination angle, that should go to like sharper or broader. Okay? Now we can hit. Refit. Oh! That's got worse. Okay. Try again. You can see here, things are being a bit funny. And that's because this is a very non-linear parameter. A lot of the other parameters are more linear in the sense of the way that they work with respect to polynomial. Whereas this one's got very, we had a way to show from the back of the room saying don't avoid fitting for this at all costs. Okay? But we're very straight on. So that's basically an initial sort of solution and exploration of pulsar binary parameters and time. So if we wanted to do more detailed study, you'll see here down here, it'll tell us a bit about the mass of things. And we don't have well-constrained binary parameters. And that's because we don't haven't done fully detailed noise analysis, haven't done So anyways, that's a brief exploration of sort of what we can do. Questions? Okay, well, okay, watch it. Okay. Okay. Well, okay, guys. Well, give it a try. See what happens. Yeah, so you just set Control C. Well, actually, before you try Control C, don't. What you can do is go up here. And I can't do it, but hit New Part. And then you look down here,